Good afternoon. Thank you for coming. My name is Alex Sutton. I'm a program manager in the Azure specialized compute team. I work on our AI and HPC infrastructure and services. What I want to do today is give you a brief overview of the range of GPUs that we have in Azure and the broad range of scenarios that customers are using them for. Kind of when we think about how people are using GPUs, they may start in one area, then quickly realize they have another business problem that can benefit from the acceleration or speed up of GPUs. They may start on the visualization side with remote desktops. They may then accelerate on HPC simulation and be able to see the results. They may start on deep learning or AI. They realize they also have a rendering problem for the corporate communications group. We really see that GPUs are applied across industries. As one example, we often go in with our oil and gas customers and talk about their HPC problems. How do I do reservoir simulation? How do I go and visualize the drill bit? And at the end, they say, oh, by the way, do you support rendering? Our corporate communication group is backlogged on their videos. Can you help us by doing rendering on demand in the cloud? So kind of my main takeaway is the use cases of GPUs are very, very broad and are applying to multiple business groups within an organization. As an example, I'll walk you through some scenarios that we're seeing in the automotive space. Kind of the low-hanging fruit is often around visualization. Think of this as VDI, remote desktops in the cloud, and increasingly engineering workstations in the cloud. Instead of having very expensive servers, effectively servers or workstations under people's desks that consume a lot of power and are very loud, move those into the cloud. Particularly as you start doing engineering around the world, those desktops can be shared. A modulo latency, but what we're finding is the latency into Azure for most remote desktop cases are actually pretty good in the US, Asia, and Europe, even coming in from multiple locations to a single area. What this is starting to enable is more collaboration with supply chain partners doing design together and securely in the cloud. The data now no longer needs to leave the enterprise's cloud deployment because you can bring the partners in, give them a secure desktop, give them access to the resources that they need, and work collaboratively. So this is very important on the front end of the engineering life cycle, as well as on the back end. If I'm doing simulations, CFD, or crash analysis in the cloud, how do I go and look at those results? I often have too much data to bring on premises or bring down to a workstation. I want to have a GPU-enabled workstation in the cloud next to the data so I can go and visualize the results. Then the last one, where maybe a broader audience, is how am I doing streaming out to many devices, gaming, video, kind of classic web streaming accelerated through GPUs. The GPU that we're providing for the remote visualization is the NVIDIA M60 card. This is the NV series of virtual machines available with 1, 2, or 4 GPUs. This depends upon how many users are using the machine, how much GPU memory do they need, and how much machine memory. We provide two types of driver types for the high-end engineering apps. Each NV 1, 2, or 4 comes with NVIDIA Quadro driver. This is their high-end enterprise driver that usually requires a FlexLM license server in order to use. One of those licenses is provided with each of the NV series apps. So that's how you can support the Dassault apps, the Siemens apps, the Autodesk apps. If instead you have more of a VDI scenario and you want to have multiple users using that GPU, you can use the NVIDIA Grid license, which I believe has five users per GPU, and then you can also purchase additional if you're multiplexing many users onto that GPU. And as I said, it's available in 3 different sizes, 1, 2, or 4 GPUs. What we're finding for a lot of customers is the memory is the gating factor. So I'm running a very high-end engineering app. 1 GPU may be fine, but I need additional RAM, so people are getting the entire box. Because of that, we're actually going to be releasing a new version, NVV2, later this year. This is really designed to address the needs of these high-end desktop users. It moves to a new CPU, whose name I'm blanking on, Skylake processor, twice the amount of RAM, and twice the local SSD. So based upon the feedback of how people have been using the NVV1, this GPU is great. The specs of the machine needed to be beefed up. So kind of moving towards the latest platform, and again twice the memory and disk, so you can choose which configuration is going to be best for your need. In terms of delivering remote desktop solutions, we have a wide range of partners, kind of ranging from the traditional thin client approach from Teradici or Citrix, where I can have a very small, inexpensive device on my desk, plug in a monitor, I'll plug in a keyboard. The desktop is in the cloud, to the other extreme of browser-based experiences from Visua or Frame. So you can provide a completely modern-based experience, browser-based, zero-code download to laptops, to tablets, to phones, or more of a traditional experience with like 2 4K monitors, keyboard, and mouse. So really being able to support the whole range of enterprise scenarios in an office to remote or mobile users. Second workload is rendering. People tend to think about rendering as something that you see in Hollywood films or advertising, but there's actually a lot of industrial use for rendering. Very big in oil and gas and visualizing the drill head going through the pipe. Widely used in automotive for styling the cars. You can take the CAD mesh that the engineers have been working on and create a realistic view of the inside and outside of the car. So how does it feel on the inside? How is reflections from the glass or the surfaces affecting the driver, as well as taking that same model of the car and using it in advertising for print, for web, or a lot of the cars driving down the roads in advertising are actually 3D rendering. So the use of rendering that we thought was going to be more on the special effects side, there's actually a huge amount of commercial and industrial use. In order to help make doing 3D rendering in the cloud easier, we have a set of plugins for our Azure batch service. Batch is kind of, think of it as an HPC cluster on demand, where it's providing a pool of Windows or Linux virtual machines, a job scheduler. You submit the job, it gets deployed out to the cluster, run, and the results turn back to you. You don't have to worry about deploying tens, hundreds, or thousands of the VMs, standing up a scheduler and handling that infrastructure. The service is going to take care of it for you. We also have licensing agreements with Autodesk and Chaos Group, so we can provide pay-per-minute licensing for these renderers. So you can obviously bring your licenses with you if you're already licensed for the Autodesk products. But if you're maxed out on premise and want to run a job in the cloud, we can provide the permanent licensing. V-Ray in particular is GPU accelerated and does a really good job on the M60s. We then got a plugin for Autodesk Maya. This is the 3D artist tool that they're doing to build the scene that they want to render. In that tool, they configure the cluster, the batch cluster that they're going to run on, submit the job. We stage the assets back and forth. They can monitor status, how is it going, seeing previews of the frame, and then get the rendered result back. third scenario is kind of classic HPC simulation. In the automotive world, finite element analysis. I'm going to go and crash a couple of cars. How is it going to stand up to that stress? Computational fluid dynamics. How is the wind going over the car, and how is my design affecting the fuel economy of the car? How do the various systems interact? What's the electrical or the electrical or RF interference in the car? The goal here is to build as few physical models as possible. How can I build a virtual model of the car, simulate a bunch of different designs? What happens if I change this part, or the structure, or the density of this? Is it going to improve my strength? Is it going to improve the crash resistance? Will it be more resistant to electrical or RF interference? Then when I actually go and do a physical prototype, I'm more likely to be right and not have to bear more expense of creating real world things. We're seeing more and more of the safety and regulatory agencies accepting simulated tests, for safety and crash. There's a lot of testing, a lot of documentation, but you're able to build better and better models of how the car is going to behave, and more importantly, how the various systems of the car are going to behave. That all of the workflow is really going digital. It's actually starting to blend more into the AI and deep learning world, where I can go and analyze the simulations that I've done, the crashes that I've done, and start to build better and better models. And instead of having everything be partial differentiation equation based, it's moving more towards AI models that, as I gather more and more data, I can be smarter in predicting the world through the AI than I can through the engineer designing the device. So it's really about, how can I digitally create the real world and then tie it into my overall workflow. Where this really gets interesting is if you can start to tie the assumptions that you made on the modeling and simulation side to what you're actually seeing in the real world through IoT. You can do what are called digital twins, have a simulation of what my car, what my industrial piece is, start to use that for predictive maintenance. What happens if I swap out this part? What are the overall systems things? And because I'm getting data from the real world, I have now a feedback loop of, was my original simulation and model right? So we're really seeing this intersection of traditional HPC and simulation tying up with IoT and building these whole new workflows and smarter ways of doing industrial design. The GPUs that power this scenario is the NC series, C for compute. Last fall, we introduced our original NC V1 was based around the NVIDIA Kepler GPU. We introduced the Pascal and the Volta last fall, so kind of two further generations. These are important in engineering because they support double precision floating point. Very important if I'm modeling, the stresses on a car, or I'm doing Monte Carlo analysis in financial services. These also are available in the same three base sizes of 1, 2, or 4 GPUs, and the compute also has a fourth size, the NC24R, where R stands for RDMA. The compute VMs have a second backend network based using InfiniBand that enable multi-GPU scenarios. This is really more for AI and deep learning than HPC simulation, but as HPC starts evolving more towards GPUs, I think we'll start to see more use of the RDMA there. Okay. Yep. So the Pascal and Volta. Third scenario is around deep learning and AI. In the automotive world, the big one that we hear about is autonomous driving. That could be cars, trucks, forklifts, drones, submarines. But it's actually a much more complex world in driving. I have to understand, what is the car seeing? How is it going to respond? What's the impact on the braking system? How fast is the car accelerate or decelerating? What's the impact on the body stress, on the torque? There's a whole bunch of simulation testing that you need to do. And when you think about when I'm doing real production scale AI at this level, I've got to develop very, very powerful algorithms that are going to use many GPUs. I've got to have a lot of data to train with and a lot of compute for experimentation. So we introduce a fifth type of GPU specifically for deep learning. This is the ND series. This is based around the NVIDIA Tesla P40 card. This is very good for deep learning because it supports single precision, floating point, and half precision. It's also got 24 gigs of local memory on the GPU. The NC cards all have 16 gigs, so this helps you run larger models or larger batch sizes of data coming into the GPUs. This is also a very good GPU for inference also, so for both training and batch evaluation of deep learning models. Like the other sizes available in 1, 2, and 4 GPUs, as well as the back-end InfiniBand network. Coming soon, we have a lot. Well, those ones have 4 GPUs. We have a lot of customers asking for an 8 GPU training option. So later this summer, we'll be introducing the NDV2, which is an 8-way, so 8 GPUs in the box, connected by NVLink, which is NVIDIA's proprietary high-speed interconnect for GPU to GPU communication. The other sizes hit bottlenecks on the PCIe bus, which is one of the reasons why we only have 4 GPUs in the box. So my only alternative for larger training is to use InfiniBand. This new size will give you 8 GPUs. This is basically equivalent to the NVIDIA DGX2 AI supercomputers. Basically, the fastest single training box that you can get in the cloud. This will initially be just the 8 GPUs, no second back-end InfiniBand network because of the way that NVLink works. Just one example of a customer in the automotive industry that's using our GPUs for autonomous driving training. It's a supply chain partner for Audi that's working with them on the chassis. So they're involved in not necessarily the core autonomous driving algorithms, but more how is the car responding? How do you think about it from a systems point of view of everything in the car that needs to be part of how the decisions are made, what's the impact on the driving experience, on the stability of the car, and the comfort of the passenger. So there's really a huge ecosystem of companies and partners working on these autonomous driving problems. We tend to hear about the very visible, sexy things of radar and LiDAR. What does the car see? There's a whole bunch of other decisions that need to be modeled out as well. To help people go and do this at scale, it's really hard. You have to worry about clusters and scheduling and data and scaling up and scaling down. We have a service called Batch AI that can be used a standalone platform service or with tools like Azure ML. It really helps the data scientist and production AI teams go and do AI training and scoring at scale. You basically say, here's the job that I want to run, this many CPUs or GPUs, here's the AI framework, here are my parameters, go. We spin up a cluster for that job or series of jobs, schedule the work, have a work crew if you're running hundreds or thousands of jobs as an experiment, make sure everything works, and then turn it off at the end. Support for any AI framework or script that you want to run. A lot of simplified experience in terms of having access to standard out, standard error, the models, the data. It's really making that scale experience easy for the data scientists to use, including storage and whatever program model they want to use to access it. This service is in preview now. We'll have some experiences with Azure Machine Learning coming soon. It was what you saw in a couple of the keynotes and breakout sessions yesterday around doing like hyperdrive for hyperparameter tuning, and any of the large-scale training at scale was done on Azure Batch. I was thinking about showing a demo, but I'm seeing that I'm out of time. I actually have a session coming up at 4:45 if you want to learn more about Batch AI and how we're using GPUs at scale for experimentation, distributed training, and other parallel type of scale-out scenarios. So thank you. It was a very quick breeze through GPUs. I do have a couple of minutes for questions on the side, and otherwise, let us know. So thanks. Let's go over here.